Welcome to my next video on roofing. I have made some improvements on my last recording, so hopefully the audio and video will come out alright this time. I have drawing 2018-07 in front of me. I do not have the measurements, so what I'm going to do in this video is just run over some sort of deductions and assumptions we can make just from the drawing itself without having any other information. So with that being said, let's get started. For this drawing, what I would recommend is to first label everything that you can. So you're going to add information to the drawing before you even start describing. So what I did was, you have two sections here, okay? And this is for obvious reasons. Section A is running through here, and section B will be on this side, right? And you can see that they are smaller trusses. So since we're not given any measurements, you have to scale every truss component, and when you scale them, you should the only thing you don't scale will be this tie beam. You can actually calculate this tie beam from that 9 to 30, and the same is true for the smaller tie beam in section B. So tie beams were not scaled. We will scale, and I'm just going to clean up a bit here. We will scale, let's call this the shorter strut and the longer strut. You scale this rafter, and you're going to scale the collar, and since it's duplicated on the other side, you don't scale twice. That would be a waste of your time. You're going to scale this kim post. For these smaller truss, it's the same story. The strut, the king post or king strut, and the rafter you will scale, and tie beam you'll calculate with the given values. You've got a collar here. Okay, so what I'm going to do, just for the sake of making things easy to interpret, we'll put your, so since it's scaled 1 to 100, I'm going to put the millimeters that I've scaled and where it corresponds to. Okay, so short strut, long strut, king strut, rafter. Same story here. Let's say that's just strut, that's king strut, rafter, collar, collar. Okay, so for the collar, for the taller, the larger truss, I have a value of 12 millimeters, and that corresponds to 1,200 millimeters after you've scaled. For the king strut, I have 46 millimeters, 4,600 in real life. The rafter, I got a value of 78 millimeters. Okay. The short strut, I have a value of 28. And the long strut was 33. Okay, those are your values. You should do this exercise before you even start tackling the measurement. In my opinion, it's better to gather all of your information at the beginning. Right, so let's move on to the smaller truss. Our collar for the smaller truss was 11 millimeters, so it's slightly smaller than a larger truss. 1100 when it comes to your description. King strut or king post, I've got 22 millimeters. Okay, your strut, I just call it a strut because there is no long and short strut in the smaller truss, you'll see. The strut I got 15 millimeters for. Oops. Okay. And finally the rafter was 45. Okay, so there is an important note here, is that there's another way to get your rafter value, and that is to take, so the two methods, and I have followed this up with the university, and I'm sure it will be confirmed, but there's a way you can either scale, or you can take that half on plan, right? And since you want a rafter value, so you've taken basically this on plan would correspond to this in your section, right? So you take half, and then you need to find a multiplier. I'll just call it x of f. Okay, and that's another method of getting your rafter value, your length. I think it is easier to scale. So I scaled everything, and I went even further and started scaling things like, I decided to scale this hip rafter. I scaled directly from plan because we've been given that, and I explained just now how I was able to scale it. I scaled this, I scaled every single thing, including the eaves. These little bits, the overhangs, wherever you see an overhang, I've also scaled that. So sort of a new discovery of mine is that if you're given a plan ratio, it makes far more sense to scale everything and find factors. So what I'm going to show you now is finding the factors. As I've said, find all the information. So firstly, let's find the factor for flat to slope. Okay. So this factor, we'll call x of f, is the application of that 45 degrees, okay? So what we want to know is, as I said in my previous video, how many, if I move 1 unit this way, how many units will this change? And since we're using 1, I can call this my x factor. Let's call it the x factor, right? So whatever we get for this x factor, since we're using 1 over here, is basically saying we can apply it to any value on flat, and it will give us a conversion to slope. Okay, so it was cos 45. So this was 45, right? That's 1 over your x factor. And we'll say your x factor is, and what did I get for that x factor? I think it was 1.4. Yeah, 1.41. Wow, 42. and I usually write as many numbers as possible because it just increases the accuracy. And then once you get closer to your final answer, you start rounding and boiling it down to a bit of a simplified number. Okay, that's your one factor, and I'm going to highlight in red here so that we know where it is. That is important because that is going to help us convert any flat value to a simple sloped value. I say simple because we're only talking about values that run perpendicular to the face of the roof. Okay, so here's the face of the roof. Any value that runs perpendicular to this face gets this value here, our x factor. Okay, so we've got our x factor to apply any of those slopes. But I went one step further in this example is I actually said, well, if we have an x factor and we apply it like that, and if we also have this value here, why can't, what is preventing me from finding a factor that actually gets this one? A factor that we can use repetitively and apply it to instances where the slope isn't perpendicular, but actually where the slope is at 45 degrees. And that's what I'm going to show you now. It's nothing new. It's the same work we've been doing. It's just that what I'm suggesting is that we get all of our values up front. So let's go from flat to 45. So when I say 45, I don't mean this 45, right? I mean 45 with regards to the angle that it's coming in. So this was flat to slope perpendicular, so let's call this 90 degrees, okay? It's coming in at 90 degrees to the face. And so this one we'll say is 45. It's coming in at 45 degrees to the face. So if you're viewing the face, this is 45 over here, okay? Flat to 45 degrees slope, not to be confused with sort of a gradient of 45. It's a different, we're talking about sort of on plan, two-dimensional. Anyway, we are going to take this x factor and let me just make it simpler to see what I'm going to do here. And it's not new work. It's basically applying it once so that we can repeat it without repeating their work. So let's just take this corner, and what I'm suggesting is that if we've got our x factor which converts 1 on flat, here's 1 on flat, right? We can all agree that's 1 on flat. This over here is also 1 on flat. Okay? I'm boiling everything down to simple units. 1 on flat, this runs up a slope, so it's going to apply our x factor, this one, okay, 1.4142. Okay, so you can see that this we can call our xy is just Pythagoras, okay? So we say this xy factor will be root of 1 squared plus 1.4142 squared. Okay, and that gives us, and if I recall correctly, it was 1.7 something. Yeah, 1.7320. So what I've done is basically laid the foundation for the measurement. We're sort of increasing the information available to us. So now we have a whole page so that when it comes to actually measuring, it's all sort of given. even though you've had to calculate it. Okay, so this factor now applies to this hip rafter, this valley rafter. Here's another hip rafter, here's another hip rafter. I'm just going to write these in nicely. And I also think what's important is to probably just understand what kind of structure we're looking at. Three-dimensionally, what would this look like? And I've decided that this entire face, okay, is actually going to be like that. And all of this is going to be the same face. I should probably not color that in because we're not going to be able to work with it. But this face is all going to be sort of merged together. Imagine taking maybe a hipped end and combining it with this face, this longer face. And what you have is the end disappears, right? Because it's joined into this hip, so you don't see it. And there's hence this dotted line is that there would have been a valley, but it's sort of been absorbed by this surface that's now become one. And so the valley's disappeared. And I want to say that this timber has also disappeared. And it has. And so I probably would not have indicated this green line, because it's just a bit confusing. Why is the green line there? Because now what the other lines are saying is that, okay, we've got a couple, firstly we've got a full truss here, we have a couple jack rafters, and it's another full truss. So it is impossible for another piece of timber to be here, right? There's no ways. So what I would say is that green line, that green dotted line, is nothing. It's maybe an indication of the travel had there been a valley rafter there. That is the line of travel, but there's nothing physical there. So basically, just ignore that green line. As far as I'm concerned, I could be wrong. We are going to now start discussing wall plates. So I've worked a little bit backwards here, but let's just draw where we expect a wall plate to be. And what's important to note here is we have a little bit of an overhang past this gable end, right? So that's a gable end, and it extends 230 mils over. So our roof covering goes past our gable end. In the previous example, we had a parapet wall. The parapet wall came right up to the top, and our roof structure actually ended here. Okay, it has to. It's a parapet wall by virtue of the name, implies that it's a wall that is extended past the roof covering. Okay, and I do not know the full history of the parapet wall, but there's a reason back when it was created to have a little wall that extends past the roof covering. It might have been for safety in areas where people access the roof, but there's a reason why it exists. And in this case, it is a gable end without a parapet wall. Okay, and that means that there is a barge board here. Okay. So let's jump back to wall plates. It's 230 over the exterior face of the parapet wall. That means you've got to come in this width, this thickness of 270. So you've got to come in again by 270. Okay. Because it's an external wall, It's a double skin with a 50mm cavity, and that means that your wall plate is going to start right over here. Okay, and now I haven't drawn it very well because the wall plate is actually only on the inside skin, so this is going to be very tricky, but it's kind of working. Your wall plate is going to run along the inside face, and it's going to go all the way to the end, okay? And then the next piece is going to run all along. And I'm drawing it because I want it to be a bit clearer as to how you can get this straight from the drawing, because I'm always quite surprised that it works, but it does work. So what we're saying is you're going to take 10650, because it doesn't include the 230, okay? 10650 starts here. You've got to subtract minus 270, okay? And now you've come to this face here, and whatever's left of that 10650 means it comes all the way here. You're going to add 500. Now you're on the outer face, which means you're somewhere down here. Okay, that's how far you've measured. You're going to take whatever is left on this side. So what I say is take 50-50, which is going to start. So what do we? Oh yeah, we took the 500. We're going to continue across. You've added your 50-50, which, by the way, looks like it stops on the outside. Okay. And so I think I would say subtract another 270 on this side. Sorry, not 270. 160 on that side. Now I could be wrong, because quite often these calculations end up sort of cancelling out, and at the end you shouldn't have done any math because it added and subtracted itself. And so often when you overthink these things, you will drive yourself crazy. Really, there's no other word for it. You will. So this face I've covered. This length you'll find on this side. So you'll take 3730, which appears to be the end of the roof covering, right? And since we know that it's 500, you've got to subtract another 500 to get to your outer face. Okay, and that's just your outer face. So now you've got to come in another 160, I would say. Here's a good example. So what I just said was you end up doing a whole bunch of maths and it cancels out. Well, here we go. This is a good example. This 3730 is there, and since we have a 45 that's running that way and another 45 running that way, what we are saying is you could just take it straight, because if I have a line there that's 3730 and this point, let's say this point travels 45 degrees a certain distance to that point there, and this end point also travels at 45 degrees the same distance as this one up here. It also travels to this point the same distance and angle. That means that the line length has not changed. Okay, so these two lines are exactly the same, and since this one is the same as 2, you're going to take 3730 as it is. Do not waste your time doing the math, because you will find out that it's the same. Okay. So that was actually that face. When it comes to this face, the same applies, is that It's a 3730 on 45-degree angle. Let's say it will run along this green line as well. And 3730 here is the same as this Y because of the 45-degree on both ends. I would say if they are different angles, if you can clearly see that maybe this slope runs like that and this one runs like that, I mean, you can see now that this outer value will not be the same once it moves along that angle. It only works for 45 because both are transformed. Both endpoints are transformed by the same value. Okay, that should make sense to you. Anyway, so you're going to take, I don't like this color, you're going to take that 3730 as it is for that face and that face, and that will take you up to there, the edge of the roofing. You're going to add that, and you see now, oh yeah, right, so because your 3730 sort of shifted, remember it was outer face over here, and since you've used it straight, it's gone and become this. Okay, so instead of taking 10,770, it's much better to take 9,770. If you take 10,770, you have to visualize that your 3,730 moved in by 500 and in by another 500. That cancelled out, and let's say you didn't have 9,770, you would say, oh, okay, I've got a 10,770, but look how far it goes. It goes over, and we already have 3,730 that far, so we have counted another 500 here, so we're going to have to remove this. This needs to be cancelled, that 500. So you're going to subtract 500 on that side, and you say, oh, okay, 10,770 also goes past that face by 500, so you're going to subtract that 500 as well. And 500 plus 500 will give you 1,000, and 10,770 minus 1,000 is 9,770. So that 9,770 is there for you to avoid doing all the math. Okay? So basically all of that calculation was to get this face, the wall plate. Because there's a wall plate here, runs along that edge, but there's, and a wall plate on this edge, but not here, because it's a gable end. Okay, and then there's also a wall plate that runs along this face. And I'm not going to go into detail because this is going to end up taking ages to do this calculation. This drawing is very long. So I want to just point out some sort of shortcuts or smart cuts. We call them smart cuts. Simplifying work so that it doesn't take so long to complete, but it's the same accuracy. And I think that's the main point of how we are doing this measurement, is it needs to be simplified and with the same accuracy. Okay. So I've explained the factors, I've explained the scaling. What ends up happening is that you've got, and I'm going out on a limb here, but I would say you can, when you are describing, you can go and describe all of section A's components. So you'll, in your measurement, you'll do full trusses for section A. Okay, and then you'll do the typical sort of timber components for your full trusses, and then you'd go on to describe your half trusses for section A, which is only this one, by the way. This is the only half truss, HT half truss, section A. Okay, and I think there might have been another, so this is also tricky, is that, okay, I'll get to section B just now. So you'll do the one method, which would be to describe everything in section A. You go full truss, half truss, you describe all your jack rafters, and then there's actually extra jack rafters that we need to point out when we get to them. That's the one method. The other method, which I think makes more sense, and I hope it's acceptable, is that you do all of your measurements in the same sort of categories of timber lengths. So you do it once, you describe it once, and you don't divide into sections. Maybe what you should do is you should divide into full trusses, and then in your little side cast description, then you say if it's in the full truss or the half truss. So what you might do is you go timber less than 2.4 meters. So you do your standard description for the timber, whatever timber that is, whatever component you're describing. It's less than 2.4 meters, and then you're going to collect, and I think this method makes more sense, is that you're going to collect all the pieces that are less than 2.4 meters. So what you'll do is you come over here and you'll say, well, what is less than 2.4? And you'll go, well, just that one in your full truss is less than 2.4. So all of these full trusses here have a collar, and there's only one collar, right, which you have scaled, and it's in this category, less than 2.4 meters. Okay. Then for your half truss, and it's important to say, it's like the half truss of section A would have a collar, but what I've said is that it was a half collar, and that half collar is 6 mils or 600 millimeters in real life. So for this half truss, I've said that basically I cut it down the center, the collar was half the full truss size, and the tie beam was half. Okay. And then I put whatever was applicable across the whole drawing. Sorry, not the whole drawing. Across, let's say, section A. Whatever was applicable in under 2.4 meters for section A, which included the half truss here and, let's say, the jack rafters, and I'll get onto the jack rafters now. I put them all into one description, which was less than 2.4 meters. I think it would be acceptable, and I think it makes more sense than to write out multiple times, and it ends up being like 4 pages of the same descriptions. I stand corrected. I'm not sure if this is acceptable, but I think it is a more logical way of going about things. So I've described roughly how the measurement was done, or how I did it. I mean, you're welcome to go ahead and write 4 or 5 pages of descriptions of timber. I just think it's a bit unnecessary. So the story with the jack rafters is that, and I made a mistake in a previous video, it is you're taking this length of a full rafter, and you're saying that 1, 2, 3, 4, 5, 6. So you're saying there are 6 dividers, but there are actually 7 spaces. So, and the way I see it is that you have to include the last one as a sort of divider, but you don't use it. So it's like fractions of 100%, and it means you must include the last value. So since the last value is 7, this full truss for section A will be divided by 7. Okay, so it's 1 times. So actually, you must be careful because it is not divided by 6. If you divide it by 6, you've divided by 1 too short. What you were saying then is that this one is 100%, but it's not. You can clearly see it would not end up being 100%, it will be short. These are both 6 by the way, so this is 6/7 of that length. Okay, and I've gone over this previously, so this should make sense now. Just be cautious of how you divide it. That's 1/7. Okay, so once I've gone over the another trick here with this drawing was that, and I'm not sure if this is correct, but I've applied this same rule, and then I've said, well, this one is 6. Basically what I did was I put all of the values, all of the multiples of 7, including ones where they go greater than 7. And I have not considered this previously, is that you could go even further. You could say a length is 9/7. You could say a length is 9/7, right? Why not? You can say that could potentially be 9/7 on slope, and I did that. So let's just fill these in. That's 7. So this one looks like 6, you can see it's in line. This one is 5, and then it gets tricky when it's the other way around. You've got to visualize that it jumped 1, and then another one, and then another one, right? So firstly, this top one traveled 1, 2, 3, 3/7, and this inside one traveled 2/7. Okay. I'm trying to figure out which one did I say was. Oh, it was this one. This valley rafter. Something interesting going on here is that these, so what I did here where I said 9/7, I also applied it to these lengths, and I'll get to them in a moment, but that's just half. But what I said was, here is, let's take this one. This is one length. Okay, that means that this one's also one length. But I said that this is over one length. And how much over? Well, we can see Phew. Okay, let's try to make this a bit clearer. I apologize for this, guys. Okay. This is one. We want to make that one. One full. Okay. And as I said previously, how many times are you dividing it by? Well, you're dividing it by the spaces, not actually the jack rafters. You need to be careful. 1 space, 2 space, 3 space, 4. There are 4 spaces but 3 jack rafters. And the reason you use spaces is because this last one is included. So if you're going to count, you must include the full length, whatever it is. So since it's 4, this is 4 over 4. 4 over 4 will give us our full length, okay? Full, because 4 over 4. This one is 1/4, okay? 2/4. 3/4. Alright, so there's nothing new there. What is new is that you could take that half truss is also 4/4, by the way, or you could scale from here. But they are different values, and I think this needs to be discussed further in class. But this value here, I should probably change colors now. Alright, this I said was one full value, so this is 4 over 4 plus, and then I just said, well, probably in line, has to be in line, I think, because of the 45 degrees. So that is 5/4 of the full length. Okay, I did the same thing to this one, and I guess it's important to have a disclaimer that I do not know if it is the correct way to do this, but it is the most logical way. I can't see any other way of doing it. So you've said it's a full rafter length plus 2/4. Okay, so it is 6/4 of the rafter length is that purple one, and I will just show you a neat trick is that it doesn't matter whether it's let's say this is 6/4 like that, or if it's, no, that's a bit long for the sake of demonstration, make it a bit shorter, or it could be like that, okay, and it could be 4 over 4 on this side and 2 over 4 on this side. This is the same value, they are equal, okay. That's what's happened here, is you've got this goes up, it comes back down, and you've made it whole, and you've said, well, it's 6/4, and you've applied your 6/4 to your rafter length, and I don't have the rafter length in front of me, but it was scaled. I scaled it. Oh, it's right, it's there. Okay, here's your rafter length, was 7,800. So that purple one is 6/4 of 7,000. It's section B, my mistake. 6/4 of section B's rafter, which is 4,500. Okay, and that is just the purple rafter. The orange one would have been 5/4 of 4,500. Okay, let's just clean this up again. So as you can see, there's actually a lot of work before you even start describing, is that you could really populate your drawing with a lot of information that would make your description a lot faster. And you might say, well, I prefer to do the description and then calculate whilst I'm describing, and I guess that's fine as well. But I would say that there's a reason why there's reading time, and there's a reason why it's better to do your, let's call it admin, at the beginning. And it's that you sort of know what to look out for. And at the beginning you say, right, here's the things I want, and I don't have them. I want a factor for to slope perpendicular. I want a factor to 45 degrees entering that slope. I want to scale everything in my cross sections. For your smaller cross section as well, scale everything. Then maybe you want to go ahead and say, well, let's find out the divisions. 7, not 6. 7. And you go ahead and you find out your divisions. And then you do the same thing for the smaller side. You find all your divisions. And to me, it's just better to do all of that up front than to have to jump between describing, then you're doing sort of analytical work on your drawing, and then you're going back to describing. I think it is better to get it all out the way at the beginning. So I think that might have been it with regards to the structural stuff. I'm trying to remember what else I wanted to mention. But I think it might be good to show you how this other y factor applies, is that, and I have asked the university and we will wait to hear from them, but if you scale this length with a ruler, because it is given that it's 1 to 100, you scale that, and since you've taken my advice and you said, you know what, Anthony, that's a good idea, I'm going to find all my factors at the beginning, and you did, and you found your factor as 1.732 on slope at a 45 degree. You say, Anthony, thanks for the advice. This I've scaled, and it happens to be, I actually forget what it was, but let's say it's X. And it's X length on flat. I've got my factor 1.732, and you have your answer instantly. It's very easy like that. And then all you do is you times your answer by 3. Okay? And the reason you can times it by 3 is, despite this being a valley rafter, it does not discriminate. It says, well, it is timber, it still runs this way. It only becomes a valley once you add a covering to it. But it is all the same to the timber. And you do exactly the same for this. You scale this one. And let's say this is y. Y times 1.732. And there you go. Get this length instantly. You do not have to redo this whole thing every time. I would prefer to set up your information at the beginning, and you get your factors, and you do this calculation, trig, and then onto Pythagoras. You do that once. If you can, if we're allowed to. It makes sense to me. And so that is my hack, shortcut. This one, I think I'm tempted to say, okay, I'll tell you what I did. So this one's interesting, guys. This one is very interesting because on first impression, you kind of want to say it looks like half. Okay, you want to say that this hip rafter, but it's, you know, incomplete. It looks like half, right? It looks like half of X. And it is not. And I'll tell you why. We're going to work with these divisions here again, right? These divisions are really useful. So not only do they help us divide a full rafter like that, but also you can see that there are nice divisions here on your hip rafter, right? So what we're saying, and remember, always put that last one in. This hip rafter in green is a 7 out of 7 hip rafter, okay? And how does that help us, Anthony? Well, it helps us a lot, because here you have 1, here you have 2, and here you would have 3. So what I said in describing this little shorter one, I said it is a 3/7 hip rafter. All right? And I think that is a fair way to describe it. It sort of makes sense. So that is that. There's one thing I think I should mention before we move on to covering and stuff like that. I see there's a ridge beam, and this is actually the first time I noticed it. I did not see it earlier. And let's just take a look at this ridge beam here. So what this orange line is saying, that's a center line, okay, or a ridge. And previously I put it in inverted commas. Yeah, it's a ridge, but it's nothing physical. Not yet, at least. And the same is true for this side. Ridge, nothing physical. But they've indicated nicely here that in green is a ridge beam, and it starts there, ends there. And what I would suggest here, and I haven't done it, so this is on the off the cuff, I would say this applies the same thing that we've been talking about, where you divide into little segments. I'm not sure. No. Yes, you can. So we'll say that this is a full length, and as I did previously, 1, 2, 3, 4. That's a full length. That means that each division is 1/4. This is not quite working out. Yeah, well, because, okay, here we go, I've got it now. So because it still works, the 1/4, but what you're actually taking, you're not taking that half truss. You are taking half of this on plan, all the way to the end, right? On plan. Take that on plan, and then you're going to find fractions of the flat on plan value, which is new. At least I think it's new. So you'll take half of yeah, let's take half of 6, so that, okay, so this length is 3025 flat, okay, and what we will say is that each corresponding jack rafter will divide it into 1/5. 1/5 2/5, 3/5. Have I made a mistake here? Yes, it's 4. Oh well. Okay, it's 4. 4/4. Phew, that is messy. Anyway, okay, so we will then apply that same rule to here. And we'll say, okay, this ridge beam travels 1/4, 2/4, 3/4. Okay, so it is almost this total, except a little shorter. And I stand corrected. I do not know if this is correct, guys. A lot of this is new to me. I'm coming up with it as I speak. So you have to forgive me, please. So that is how I would approach that question. I don't see how the information will come from anywhere else. Maybe I'm just being stupid. But it looks like a perfect firstie, and the reason I spotted it is because it follows the exact same behavior that we've been taking advantage of, right? It's doing the same thing. It's lining up exactly with a division. And if it didn't line up, you couldn't do it. You couldn't take the 3/4. Anyway, that is everything for the structural components, I think. There might be more. I don't really recall any other tricks that are worth mentioning. I've previously described how you do all of those jack rafters is the division method. And then what I'd actually do is to get all the values up front so that you know where to group them according to your standard system. So less than 2.4, 2.4 to 3.9, or 3.9 to 6.6, right? And what I ended up doing was get all of these values up front, and it's a long exercise, but just say, I think it was maybe these that end up being less than 2.4, I'm not sure, and then I think it might have been this 1, because that looks like, yeah, that's times 2, times 1, times 2, times 2. So those might have been grouped, and then I can't remember the rest, but you end up grouping them. But do it in advance so that you can see. So what I would say is, if this, what was this division? I think it was 7. 1, 2, 3, 4, 5, 6, 7. So I would go 1/7, 2/7, 3/7, 4/7. So basically I did an inventory of all the jack rafters before I even did the description. I said, okay, 1/7 of whatever this full raft length was, and I would put in a value. I put in a value equals x equals 1.4x, and this equal 2x equals 2.5, and let's say you get all of these values, okay? And once you've got these values, it's quite efficient to say, okay, there's there's only 2 instances of a 1/7. That's there. Okay, and if it's less than 2.4, it goes in here. Okay, and then you go into your 2/7. You say there's 1, 2, and another one there. So you say there are 3 instances. 1x to 3 times 1.4x. 3 instances of this one, and you'll group it accordingly. And I think they might have both fitted under your 2.4. And then you move on, and you end up doing this quite fast. It does not take, don't spend longer than you need to on these things, because time is very precious. So that is how I approached the jack rafters, because there are a lot. I try to batch the calculations so that you just rattle them off. You do everything in a big group. You organize it nicely so you can understand and reference it, and then you add it to your description. It seems quite a lot faster than if you were to do them individually. And I hope you aren't doing them individually, because it is very slow. So put them into one big group, and just basically print it out. And finally, when you get to describing, you get to just plug them into your categories really fast by looking here. And what I would say is, label your drawings so that you know what's going on here. 1, 2, 3, 4, and you will know that just means that you're multiplying it by a 7th of, so that's 3/7. And yeah, I guess that's enough about the jack rafters. Let's move on to roof covering. I don't think there's anything particularly interesting to say about roof covering. I will say this though, I see that they didn't describe the or at least you couldn't see the tilting batten and the battens, so, or the tilting fillet and the battens. So what I did was I just assumed it was I think it's 345 again. And I said, well, 345 will fit into the 500. And remember, it's 345 on slope, so you actually have to consider that it's a bit shorter because it's on slope. So it definitely fits in. So what you'll say logically is that you can fit 2. And those 2, the first one would be your tilting fillet, and the second one would be your batten. And that is yeah, that is that. In the absence of any evidence, you make the assumption, right? Because it's a tiled roof, we'll take this span. I stand corrected. That could be different. And in your spec, so you don't actually have a description for your tilting fillet. So what I said was it is a 38 by 50, same as the previous example we've worked through. And tilting fillet on the outside, and with the 50 mils upwards to allow that tile to be pushed up a bit more. And then your batten on the inside in yellow. As for the rest, it is pretty straightforward. You just taken, so for your roof covering, you just taken that side, you multiplied it by your gable end, and remember at the end of that huge description for a roof tile, you need to apply your factor, which I've put down here. And remember, don't use this factor. That's for your rafter, your hip rafters. So you must use this factor for your standard rafters. And at the end of that giant tile description, you add times 1.4142, turns the whole thing into slope, like this. And as I described previously, just does not matter if it's like that on slope, mono pitch, or like that. Is the same thing, exactly the same thing. Okay, so you times it by one number, and it's all it's saying is, well, this happens to be traveling all in one direction. This one, it's sort of a change in direction, but it doesn't change what is happening with this flat dimension. the flat dimension is still having to convert itself by 1.4142. Same story here. This flat dimension still has to convert itself to get to that. It is not concerned with what exactly is happening with the roof, but it's only concerned with how it needs to transform itself to get to this slope. Okay? I don't know if yeah, it shouldn't keep you up at night. So that is the roof tiles. The ridges are, so a lot of these values, once you found them for the structural items, you just plug and play, you copy it across. So let's just keep my factors in a nice neat box. So a lot of these values you copy across. So for your hip rafters, you just take exactly as you'd use for your structural components, the same. So remember, that's a valley. So there's one trick there, right, is that when you come to describing your ridge tiles, you might be tempted to say, well, you previously had three hip rafters for your section B. 1, 2, 3. And if you're in a rush, you might forget that this one is actually a valley. So you can't, so with a lot of stuff you can plug and play and copy across, and that's when you get caught out, because this one you can't. This is a valley and it does not get a ridge tile. So that would catch you out if you're racing, you know. So you must be aware of these things, and it's probably best to label them as well. That's interesting. I've just noticed that is downpipe. I didn't realize. I was trying to figure out where all the outlets. So in this example, DP must be downpipe, okay? And by virtue of having a downpipe there, we have to assume there's an outlet, and well, that solves a lot of problems for me. I had no idea where the downpipe was or the outlets. Okay, we will get to that anyway. So that's the trick there, is this is a valley. It does not get a ridge tile. So you apply a ridge tile here, which is straight from previous values. And that's also from your previous value. Of course, ridge tile along there. And yeah. Okay, so when it comes to finding this ridge tile length, it's from that end right to the edge of that sort of barge board to this inner face, and the inner face is tricky because it's 500 over the 10, and the issue is that the 500 does not take you to the inner face of the brickwork, it takes you to the outer face. So you're going to have to add, and maybe this is the wrong technique to apply here. So you could do that, you could add the 270, or you could, I'm not sure. I'm kind of thinking about these spaces again, and then making a rule. Let's say this is 11 spaces. I'm thinking of actually taking one of these, maybe taking this length, and remember we said it's 1/7. Maybe this is 12 spaces, so it's 12 sevenths of this RT. Maybe this value needs to be sort of divided by the components again. in a sort of roundabout way to calculate that ridge tile length. It's not what I did, but now that I'm looking at it, it doesn't. Do you see what the issue is here? Is that this does not necessarily line up with that wall, and what makes it worse is that I think we made it a full. Yeah, you see, it doesn't actually line up. So I would say if you want to be really creative, do that sort of spacing division thing, but take a known value. Let's say you could use this full rafter. You're going to take the divisions again. I'm confusing myself now. Yeah, so you're going to take the divisions again and then multiply it by how many divisions there are on this side. And that's sort of a foolproof way of calculating these things. There's no ways that could be wrong, in my opinion, because of the 45 degree. I could be wrong though. I could be wrong. So that would be your ridge tile. We'll move on to that special piece, that purpose-made tile that goes on the corner. Not on the corner, on the intersect. I see the description is quite specific to say it is the intersect of the valley hip rafters and ridge, or ridge and valley hip rafters. So here's an intersect between a ridge and hip rafters. Sorry, did I say valley rafters earlier? Ridge and hip rafters. So there's one there. It is not one there because this is sort of a red herring in the drawing. This green dotted line is sort of going to throw you off, so you just ignore that green dotted line. And I'd say there's another purpose-made tile over here, right? So there would be two, but now, yeah, I was about to say that there are different size tiles, but you will see that I think there's enough flexibility in the description to allow you to include them together. So you can just say two, because it's purpose made. That wording, purpose made, implies that despite this one being bigger and this one being smaller, you can still say times two, because whoever's designing these and making it will account for the size differences. It's purpose made for that intersection. So this is a rare example where you can include things that aren't the same size and the same description. I'm not gonna. Okay, so we've done our intersection, we've done our ridges. Should we do? Let's do flashing, cover flashing. So, the previous example, we had a roof that came up to the gable end and stopped. As you can see, this goes right over the edge. So there is no flashing and cover flashing in this example. Okay. I think that covers everything. We're going to eaves and verges now. And I'm just, yeah. So for eaves and verges, what I did was I used this factor again to firstly find out which ends, how long is this distance? How much of it is exposed? And there are two ways of doing this. The first way is to scale it, and it's the faster way, by the way. So I'm sure you'll be interested to hear this. You could scale it from the furthest point to the furthest point, and then apply your factor, which was this one, X factor. That's the faster way. The slower way is to take the 500 and, well, you do the square, make a little square, you say this is 500, this is 500, you got to do a dotted line, and you say, what do I need to do to get it on slope? So basically this technique is a repetition of the factor method. It's just more specific. The factor method uses 1 as a unit, and so what you're saying is 1 can turn into this, and 1 here will turn into this, and that gives you the ability to convert anything, which I think is much better way of doing it. So that is what I did. I scaled it and then I applied these factors, and then you get, I don't recall the actual value, but then you apply these values here, and what is quite important to make sure you don't get caught out by those ends are longer, okay, because they're now actually going to use this factor. So you need to recognize, because it is part of this hip rafter that used factor Y, it also means its ends need to apply the Y factor as well. You can't apply the X factor to the corners because they're traveling on a 45-degree angle, and it's slightly longer. Okay, so, and the other thing is, I'll just explain, here is the revealing part as to what needs to happen. Why are these exposed with creosote? Well, sorry, why are they treated with creosote? It's because they're going to be exposed. And also in the diagram, you don't see a covering, so you say, okay, it's exposed. That means you're going to have to saw, it's going to be sawn and shaped, and that'll be that one description. You're going to apply your factors, like I said, and you're going to find these lengths, and then you apply your other factor for this one. You're going to treat it with creosote, and what I did is I put the description for creosote after I did all of the other work. And I'll get to that creosote calculation. Fascia boards and barge boards, pretty straightforward. It's from the plan, and it's on flats, so there's no special calculation here. Just remember that when you come to your fascia boards, it doesn't say PVA paint, so you're going to have to do the calculation 2 times 12 and 2 times 225, and that's your perimeter that needs to get the PVA paint. Okay, I think that is fairly straightforward, and I'm going to move on to the creosote. And the creosote is quite a big calculation. The description is pretty short, but the calculation is long because you have perimeters of multiple exposed timbers, and the worst part is that it's not all clear on drawing what is exposed. So we've already did a little bit of investigation to find the tilting fillets and the battens, and then further investigation for the rafter ends and the hip rafter ends. So there's quite a bit of timber that's actually exposed here. There's a long calculation. This is a tilting fillet. Okay, this is a batten. So on this side you already have 2. You can see that. Okay, in a different color. And this is just for the sake of indication of how much you need to measure in this example for creosote. Okay, you've got your 2 your hip rafter ends, okay, and then let's do an orange. We'll have a whole bunch of rafter ends as well, normal rafter ends. And thankfully these measurements changed. Thankfully these have previously been done when you did your wrought and shaped ends. So you should have, I think it might have been 700 mils and 700 mils for the rafter ends, and then I'm gonna say that this one, I don't remember the exact number, but let's say it was 800 for your hip rafter ends. Okay, so thankfully you have the linear dimension, but you don't have the perimeter dimension for these things. So you'll just copy across your linear. So it's X. Oh, sorry, I actually have an example. So I'll use what I've said. So let's say it's 700. So you can just copy across 700, and you've got to find the perimeter. What is this? Rafter end. So you're going to find the perimeter of your rafter end, which was 2 times 38, 2 times 1.5. 2, okay, and then you get your perimeter, and then you apply it here. Okay, same story for the areas where you have a hip